Hello, in this video we are going to explore what metamaterial polarization rotators are, how we can obtain the polarization rotation from metamaterial structures. If we consider a transverse electromagnetic wave, polarization refers to the direction of the oscillation of the electric field. So any device which can manipulate this orientation is known as polarization. So usually the polarizers are bulky in nature. So this is one of the patterns showing some of the polarizers. You can see that these structures are bulky. So here, by using the metamaterial structures, it is very easy to produce ultra-thin compact size, wider bandwidth, and highly efficient polarization rotators. That's why metamaterial found lots of application in designing the polarization rotators. So the polarization rotator consists of a periodic array of asymmetric patches. So this is one of the example of a polarization rotator. So there will be two types of polarization rotator. One is the reflective polarization rotator. Second one is the transmissive polarization rotator. In case of a reflective polarization rotator, the structure will be backed by the metallic plate. We know that means for the reflection to occur, it has to be backed by the metallic plate, and the polarization conversion occurs during the reflection. So if we have a bipolarized wave, that is a vertically polarized wave incidenting on this metamaterial polarizer, the reflected wave will be horizontally polarized. That is, it is converting one form of wave to the orthogonal polarization. And in case of a transmissive polarization rotator, polarization occurs in transmission. So this structure is not backed by any metallic plates. And if a vertically polarized wave is incidenting on it during the transmission, it is converted into horizontally polarized wave. And for both reflective and transmissive polarization, for this polarization to occur, they are using the asymmetric patches. Let's see why we are to use the asymmetric patches for the polarization rotator. So to give an idea about why the polarization and symmetry are related, I'm taking a common example. We all are familiar with antenna cases. So consider a square patch antenna. We know that the polarization that we get from this antenna is linearly polarized. When we observe this antenna, we know that it has a four-fold symmetry. So if we want to obtain the circular polarization from this structure, what we usually do is we will cut the opposite ends. So it will be like this. By cutting the opposite ends, we are making this structure asymmetric. By making the asymmetric structure, we can obtain the circular polarization from it. That means that we are disturbing the linear polarization by introducing some asymmetry to the structure. That is how we are obtaining a circular polarization. So if we have to obtain or manipulate the polarization, we have to introduce asymmetry to the structure. So this is just an example to give some idea about how this polarization and symmetry of the structures are related. Let's check how the asymmetry causes the polarization rotation in metamaterials. So first I am going to consider a symmetric metamaterial structure like this. So here you can see that this structure has a four-fold symmetry, and I am going to consider a bipolarized wave incidenting on it. You can see that a bipolarized wave is incidenting on it, and this is the polarization of that wave, and I'm going to split this wave into two components, U and V components. Here you can see that as it has the fourfold symmetry, both the U and V component, U component along this direction and V component along this directions, will be having the same response. So they will cause the resonance. That means after the reflection or the transmission, both the U and V component will be in the same orientation. So this is the reflected or transmitted wave. So here you can see that both the reflected U and V are components are in the same direction as the incident wave. So it will provide a copolar wave reflection itself. So if we are using a symmetric structure, there is no polarization rotation. So now I am going to consider an asymmetric structure. Here you can see that the wave is not symmetric, fourfold symmetric. So here also I am going to make an incident wave of bipolarized wave. Here you can see that this bipolarized wave is incidentting on this structure. So here also I can divide this bipolarized wave into two components, U component and V component. Here you can see that the U component will behave in the same manner as the incident wave, but in case of V component, it will be oriented in this direction because of the asymmetry. This will cause the 180-degree phase reflections. You can assume the wave in this direction, and because of this orientation, it will cause 180-degree phase shift. So here you can see that upon reflection, U component will be in the same orientation. So here you can see that the U component are in the same orientation, but because of the phase reflection due to the asymmetry, the V component will be in the opposite direction. So the V component is in the opposite direction. So the resultant direction of the wave will be along the x-axis. That means the resultant component of the wave is horizontally polarized or x-polarized. This explains why an asymmetry in the structure is producing the rotation of a y-polarized wave into an x-polarized wave. Hope you get the concept how the asymmetry is introducing the polarization rotation in metamaterial structures. So I included this picture to give an intuition about how the polarization rotation works. So I hope you get some idea from our previous slides. So this is the incident field and it has U and V components. So it has U and V component, and upon reflections, it will be having U and V component. So U component will be in the same direction as the incident U component, and the reflected V component will be in the opposing direction as the incident V component. So the resulting reflected or transmitted wave will be along orthogonal to the incident direction. So you will be seeing these type of pictures in most of the publications. So this will give an idea about what this actually means. So if you have any doubts regarding this, please comment below. The parameter used to measure the efficiency of the polarization conversion of metamaterial is defined as polarization conversion ratio. So it is defined for both reflective polarizer and the transmissive polarizer. So in case of a reflective polarizer, we know that when a bipolarized wave is incidenting on it, it will be orthogonally polarized while reflecting back. So that means if a polarized wave will be converted into an x-polarized wave upon reflection. So depending upon the efficiency of this reflector, there may be some y component also in reflection. So the polarization conversion ratio is defined as the ratio of cross-polarized reflected power to the total power. That is, it is equal to Rxy the whole square divided by Rxy plus Ryy the whole square. In this case, we know that if this polarization rotator is ideal, that is, then this case, this Ryy will be 0. So all the wave will be converted into the orthogonal polarization. In that case, PCR will be equal to 1. So the same will hold for the transmissive polarization. In case of transmissive polarization, when Y-polarized wave is incidenting on it, it is converted into an X-polarized wave. So it is defined as the ratio of this cross-polarized transmitted power to the total power. Here in this case also, if this metamaterial rotator is ideal, this component will be 0. In that case, PCR will be 1, or it has 100% efficiency. And these are some of the things to be considered because this polarization conversion efficiency is affected by the loss in the dielectric because the transmitted or reflected power depends upon the loss. So to get the 100 percentage conversion ratio, it is better to use low loss substrate while designing the metamaterial converters. This one was included just to give some idea about how the CST simulation is done for the reflective polarization rotator. So you can use the frequency domain solver and you can use unit cell boundary conditions and means in distance to reference plane you can use the de-embedding distance. And one important thing is you have to use two Floquet modes because we have to consider both X and Y polarized wave because the Y polarized wave is getting converted into X polarized wave or vice versa. So we have to analyze two modes. So here you can put two. So in CST, these X and Y polarized waves are defined by TE and TM modes. After the simulations, you will be getting results like this. From this, you will get the result RYY and RXY. And using the previous equation for PCR, you can calculate the polarization conversion ratio. To get some idea about TE and TM mode of excitation for the periodic structures, you can watch our EMC simulation video. I will put the link in descriptions. I think that's all. If you have any doubts, please comment below. Thank you everyone for listening and all the supports.